Just as in the univariate case, we talked about x having density fx. In the bivariate case, we can say x comma y, these are two jointly distributed random variables. This pair has joint density or joint probability density or joint PDF fxy. It's a bivariate function. There are two variables x and y. Now, what does this mean? This means that whatever a and b you take and c and d you take, a less than or equal to b, c less than or equal to d, this probability that x lies in this interval and y lies in this interval equals the integral of fxy over that appropriate region. Pictorially, this means x lies between a and b, y between C and D. So the point x comma y lies in this rectangle. Now if I think of this as its graph, which is a surface over the xy plane, and it is non-negative, so it is above the xy plane, in that case this integral is basically the volume of the tent with this as the floor and this surface as the roof. So here is the surface and here is the tent whose volume is given by this. Now, thanks to the probability axioms, I can combine countably many such rectangles to produce more exotic floors. And in this way, whenever I take any region which can be approximated by a countable operation of rectangles, I have the same idea. So if I take some shape S, which can be expressed as some countable operation involving just rectangles, then the probability that the point x comma y belongs to S is integral of this fxy over this set S. Now you have to convert it into suitable iterated integrals and then work out the volume. Now let us talk about two properties that a joint density must satisfy. Property number one is that for all xy, fxy must be non-negative, which is quite natural because we are integrating it to get probability, which has to be non-negative. So that is condition number one. And property number two is if you integrate from minus infinity to infinity both over x and y, then you should get 1, which is very natural because this is nothing but probability xy both lying between minus infinity to plus infinity, which has to be the case because these are both real valued random variables. Every real valued number, so every real number must satisfy this condition. So this is a sure event and hence this is equal to 1. Incidentally, when we say that probability of x lying in a to b and y from c to d is given by this iterated integral, we are integrating over y first and over x next. This order is not important because this is a non-negative quantity, so you might as well integrate first with respect to x and then with respect to y, like this. Let's work out a simple problem. I tell you that here is a joint density which is a constant c if x and y both are lying between 0 to 2 and otherwise it is 0. You have to find c. So this density is a constant over this square and 0 outside. Now if you think of it as a surface, it is like this. So this square is this square and it's a constant at height c and it is 0 everywhere else. So when I have to work out c, I'll use the property that since it's a joint density, so the total volume under it must be equal to 1. In this case, that volume turns out to be just the volume of this box. So ideally do not need any integration. I know how to find out volume of a box. This side is 2, this is 2 and this height is c. So I need for C to be equal to 1, which means C has to be equal to 1 over 4. And that's the answer. In this problem, I am giving you a bivariate density fxy, which is a constant, some c, if x square plus y square is less than or equal to 2 and 0 otherwise. Now I tell you that this pair of random variables has joint density this fxy, then your job is to find the value of c, the numerical value of c, and also this probability.